Okay, makita ninyo ang attendance sheet na to.
Yes, sir.
Yes, sir.
Gitara, sir.
Okay, Abarkis,
Present, sir.
Abrasaldo,
Present, sir.
Anchita,
Present, sir.
Arong,
Present, sir.
Barrios,
Present, sir.
Bilbistre. Absent Bilbistre. Kanyete. Kanyete wa duha na yung absent niya. Caballero,
Present, sir.
Castañares,
Present, sir.
Clemente. Clemente. Coyos,
Goyos, present, sir.
Takay,
Present, sir.
Diglasa,
Present, sir.
Binopol,
Present.
Durham. Durham. Scario,
Present, sir.
Ike,
Present, sir.
Burua,
Present.
Iliana,
Present, sir.
Arina,
Present, sir.
Groma,
Present, sir.
Leopando,
Present.
Luab. Luab,
Present, sir.
Lumibaw,
Present, sir.
Yuli. Yuli wala. Murok,
Present, sir.
Nervida,
Present, sir.
Alice,
Present, sir.
Pipito. Pipito wala. Perez,
Present, sir.
Das,
Present, sir.
Ponte,
Present, sir.
Robin,
Present, sir.
Sanoy,
Present, sir.
Sinilio,
Present, sir. Sinilio.
Suson. Suson wala. Toledo,
Present, sir.
Gara,
Present, sir.
Yaon.
Present, sir.
Okay, kisa may naabot na.
Clemente, sir.
Clemente, who else?
Belvestre, sir.
Pilbistre. Kinsa pa? Wala na. Kanyete, Durham, Muley, Pipito. Suson.
Na si Pipito, sir.
Nas Pipito? Sige.
Na.
Suson. Okay. We have 4 people, no? 4 student absent. Okay. So, we are going to finish first our mole balance, no? Supposedly, I'm going to discuss this PowerPoint, but then malaka tong time, so ako na lang ning ihatag sa inyong PowerPoint nato in PDF form, and then doon naman po dire atong assignment, no? We have our assignment here, which is posted in the last part. This one, no? Assignment nato ni, no? This is not a quiz, this is an assignment. And also we have an assignment. Kusara ba to ka assignment? May solusyon eh. Okay. Okay, assignment po din siya. So we'll take out this one. Not this one. So assignment sa duha, tulo. Okay, we have 4, no? We have 4 assignment to solved. No, I'm going to post the assignment inbox sa ato ang module course na to, and then you are going to submit that on Tuesday. Tuesday ninyo i-submit, no? Right away after our discussion, mag-post ko sa to ang module course sa assignment inbox, no? Um, the assignment will be posted. Ako na i-upload sa to ang file, no? Ato na lang mo pangita sa tong file sa to ang. Okay, I'm going to put this sa MS Teams o sa course module kini atong PowerPoint, no, para makita ninyo. Okay? So dili na ako ni discuss because ang tanan na ana sa ato sa video discussion sa chemical engineering guys, no. Tanan niya gi-discuss niya bahin aning sa mo. So after these things, maybe tomorrow Friday mag-discuss na ta sa ato ang recall sa ato ang kinetics, no. Chemical reaction kinetics, and also the moles balance na. So kini siya mas balance pa man din. We will work on the mole balance na, no. Sa Friday ta mag-start. Okay? So by Monday we will have our first quiz. Okay, so post ko na lang ni siya. So we'll start sa ato ang tiwaso na to ato ang discussion sa mass balance, no. Okay? So mo na to ang kuan, no. Nag-intad tong sa part sa kuan sa four videos no, sa third video, so ako na lang gibali ng fourth videos here, no.
What's up, guys? It's chemical engineering guy, and we're going to take this mass balance course to see the topic on diagram and flow construction. Diagram flow construction. In general, it's how to construct a diagram that shows all the flows, process units, and essentially how to do it. So before, probably you've seen, we saw 3 examples about the distillation unit and about mixing unit. And I think the last one, it was a semi-batch. It was about a tank that was evaporating hexane. So if you haven't seen those, please go. It's one video before. You will understand the need of the construction of diagram flows. And these are just like general rules how to do diagrams, so let's do it. It's so easy to construct, just go to the basics and you will never get lost, because we need actually like a standard to know when are we, that you can read someone else's diagram, you can go to internet and understand the diagram, etc. So in general, you will see a text so telling you all the problem, like a verb. They will see you evaporate, you dehydrate, blah 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 blah. All these things are not that useful, or at least I think it's more useful if you organize the data and then draw it, like draw an actual diagram. I think it's better to see, if I tell you there's like this here and I fit it here and then it goes here, I think it's better than just tell you like there's a column about, I don't know, 50 meters and you need an inlet here, and we're not going to do that. Well, actually, we are going to do that, but what we are going to do is to draw that concept. Now, we're going to treat these unit operations, for example here, this distillation unit, or dehydrator, or whatever it is, we're going to take it as a unit operation, and we're going to call these boxes. What is a box? Is nothing more than a block which represent a unit operation. The flows or streams will be the arrows showing the direction of the flow. It doesn't matter the size or direction of flow. Just, of course, that if you connect one arrow to a box, you're saying it is going inside, and if you connect an arrow to another thing like disconnected, you are telling them that you are not having an inlet but an outlet. So doesn't matter the size, doesn't matter the width, doesn't matter the length, etc. You just need an arrow to show the direction of the flow. Normally we're going to label up here the name of the flow, F, with the total if you have it. And down here we try to use the composition of the flow, composition, sorry, doesn't work that much. The composition of the flow. So you have, for example, water, sulfuric acid, and table salt. Just look, what is this? This means weight of water per weight of solution or mixture, whatever you want. But what does it mean is this is mass fraction, because sometimes you will have mole fraction, so it's not the same, you gotta change it. And right now we don't take care about temperature and pressure, but in chapter 5 you will actually need the temperature and pressure, especially if you are dealing with gases. So guys, let's continue. The general rules that I recommend is taggage, equipment, and arrow. So don't let just flows everywhere. And sometimes this flow actually is important. It connects. Why just let it here? Why don't label M1, M2, and M3? Or equipment, don't let blocks alone, please. You are mixing, there's always a mixing unit. Even though it's like piping, but there's something special there mixing. Please assign variables to the unknown. If you don't know that, just assign it as a variable. You have airflow, just tell F. You don't know what is it, just leave it alone. You have this data, just write it down. Avoid excess of variables, please. It will help you a lot. For example, if they tell you C is the half of the inlet F, don't use C, just use half F. For example, I have this, I have F, C, and D. Why use C when we can use 1/2 of F? It's better, I think. If you can do it, okay. Or if they tell you A is equal to the flow of the distillate, which doesn't make sense, but okay. If they tell you A, E is equal to D, you could actually say E it's equal to E, which it, or to D, D, and D. You just have one variable instead of two. So, okay, avoid excessive variables. Use the same units to avoid error, confusion, and conversions. So I rather convert everything and then write down in the stream than having the stream with, I don't know, moles and the stream in pounds and mass, like kilograms, tons. So I rather do everything before, and I don't know, if I'm working with kilos, I write down kilo. If I'm working with tons, I write that ton. You have the data in grams, I need to change it to tons. I have the data in pounds, I need to change it to kilograms, etc. And finally, we are going to do an example. I give you time to pause the video so you can read it. And we continue. An experiment on growth rate certain organism requires an environment of humid air enriched with oxygen. 3 input streams are fed into an evaporator chamber to produce an output stream with the desired composition. So A, liquid water is fed at a rate of 20 cubic centimeters per minute. B, air, which is about 21% of mole of oxygen, and the rest is balanced. And C, pure oxygen with a molar flow rate 1/5 of the molar flow rate of the stream B. So it's 1/5 of B. Good. The output gas is analyzed and is found to contain 1.5% mole of water. Draw and label a flow chart of the process and calculate all unknown streams and variables. So we're not going just to draw the diagram. We're going to actually calculate the answer. So remembering, we have water here, we have this outlet, and we have an inlet. They tell you this one is 1/5, which means is 0.2 here. And, well, okay, let's say Q. Water, okay, we have all the flows. In F, let's go for the compositions. I recommend going first for the flows and then going for the compositions. You know, water is of course 100% water. So we're going to put the volumetric flow of water. And F is very much interesting. You have 1.5 mole of water, which means there is 0.015 gram of, well, moles of water per mole of solution. Then you have X, an unknown, of moles of oxygen, and this is the thing I told you, avoid, instead of using Y, let's use 1 minus X, which makes sense. Well, it would be 1 minus 15, sorry. Just to let you know, Y plus X plus 0.015 will give you 1. So let's use, if we wanted to substitute Y, something about this. Oh, sorry, no, it's a minus. Minus, minus. So instead of using Y, we can use this here. That's everything. We're actually not solving. I just wanted to show you how to label it. The solution, you can find it here. Go to this web page and you can search for the courses and then choose mass balance. And I have a mass balance problem section, solve section of chapter 4, which is the one we're studying right now of Felder. But yeah, that was in general. Let's continue with the exercises. They label you this one and they tell you calculate N, which is pounds moles of methane, which will be this one right here. It's very easy, just 0.3 pound mole of methane per each pound of solution. And we have 100 pounds of solution, so you just need to multiply these here times this, and you will have 30 pounds mole of methane, which makes sense because if you have 100 moles and you know 30% of them are methane, makes sense 30 pounds mole methane are contained in there. Now they ask you to calculate the mass, not moles, but mass of C2H4. We need to calculate first the moles. So we do the same process we done before, 0.4 times 100, you get 40 pound mole C2H4. Now, how do we change moles to mass? Easy. We just need the mass, the molecular weight, which is 30 pounds per each pound mole. So you multiply it and you get this value here. 1,200 pounds of C2H4. Nice. Now we continue this exercise 2. They tell you calculate the flow of M, that means toluene, in terms of X. So they don't give you numbers, they just tell you to let everything with variables. Please ignore this. Now, you know the flow times, this is the amount of toluene entering, it's F, let's say this is F. And we say 1 minus X because X, they tell you, is benzene. 1 minus X is Y, toluene. So we could use Y times F, which is exactly F times 1 minus X. They give you 250 kilograms per hour, which we already have. This is here. And we're changing hours to minutes. So this hour takes this hour, and we will have the kilograms per minute. Here it is. Nice. Good. And finally, we have this stream. They tell you to calculate N mole of CCl4. So number one, we need to find the specific weight of the solution. They give it to us and they tell you 1,595 kilograms of CCl per cubic meter, no, cubic milliliter, no, cubic centimeter, which is, no, ignore, sorry. It's kilograms per cubic meter. CL4, sorry guys. Now let's calculate the mass. It's simply density times volume. Density is this data here. We put it right here. Times volume, which we know it's 75 milliliters. We know that 1000 milliliters, hopefully you know it, it's 1 liter. And we know that 1000 liters, this is not that common sense, but try to learn it. 1000 liter is equal to 1 cubic meter. So what we're going to do here is liter goes with liters, milliliters goes with milliliters, and cubic meters take out the cubic meters. So you are left with only kilograms. Doing the math, you get this. Now finally, we have mass, we have molecular weight, we can calculate moles. So just divide with the molecular weight and you get the answer. How many kilomoles of CCl4 are in 75 milliliters of CCl4? That was everything I wanted to show you about diagrams, how to construct them, don't get lost. A good tip I show or tell is always do large and separated lines so you can add data here and here and here, because if you do like 3 streams are going out and you don't even have space to write. So try to do the biggest flow diagram you can do. So see you in the next video. What's up, people? It's your chemical engineering guy, and we're going to continue with the mass balance section or course. We're going to talk about the general information about how to construct a mass balance. And for this, I'm going to talk about the scale up or scaling up when you're like in a plant and you go up, you need to increase your production. How do you do it? Or at least how do the math in the mass balance works? And we are going to see also what the hell is a basis of calculation. This, as it sounds, is just a base number to do your calculations. But okay, now you've seen diagrams before. We already see how to construct diagrams. So you haven't seen them, go back, please. You will understand better this video if you know how to do a flow diagram. So we're going to see some diagrams here, and I ask you kindly to review them and try to understand them. In every one of these, there's a basis of calculation. Don't worry, I'm going to explain it later. This is a basis number that we assign it to simplify the problem. So for example, imagine this problem. I will read it to you. The typical text will be benzene and toluene are going to be mixed and each flow is equivalent. So you have the same amount of benzene entering and you have the same amount of toluene entering this mixing unit. The product, which is P current, will be of course 50% benzene and 50% toluene. So the problem here is they don't give you data. You have no numbers, they just tell you these ones are equivalent. So what normally engineers do, or people that design, they choose a basis. I would choose a basis. What basis? Well, let's continue. I would like, I don't know, if I would like to say 1 kilo of B, because it will be the same kilo than T, then of course you could do the mass balance and get that P equals 2 and the composition stays the same. So we could also say, like I want to choose 2 kilos of P or 1 kilo of P, and you could solve this. If you choose 1 kilo here, you will have, of course, half kilo here of benzene and half kilo here of toluene. So I think you're getting to understand that it doesn't depend on the number. It depends more on the relationship. It must be balanced. If you balance this, you're going to be okay. What will happen if we have this exact system here? We have 1 kilo here of benzene, 1 kilo of toluene are entering the system. Everything is fine, same composition, and we have 2 kilograms of product. But let's say this is just a pilot plant, and then your boss tells you, hey, I like it, it's cool, you're mixing units, it's fast, I like it, cheap, let's do it, but the problem is that I need 20 kilos of product. So how do you get those 20 kilos of product? It's easy, you only need to divide the 20 kilos of product with the actual amount of kilos of product, which is 2, and you will get the factor 10x. You just need to multiply every flow times 10, which is easy because in this example, we only have 3 flows. And 2 flows are equivalent or equal, so it's easy. So 1 times 10 gives you 10, 1 times 10 gives you 10, and 20 or 2 times 10 gives you 20. So that's cool, your boss will be happy because you have the same product. The product hasn't changed, it's half and half, just the amount, which is very cool because you can sell a lot more. So let's continue. But what about, I don't know, If we're doing this, you know you did this for, let's see, for your experiment. And your boss tells you, please, like, tell me how much time do I need, or how are the flows, how much product are we going to get per hour, per day, per year? Please tell me, because it doesn't make sense if you have this process and you need 10 years. Well, very welcome, but no one will buy it. So we need to add some units. You could use, I don't know, per minute. And well, of course, this was 10. Sorry about that. It was 10. We were about the 20. It was 20, 10, and 10. So what we are doing is only saying that we are going to do this per minute. So the numbers are the same: 10 kilograms of benzene, 10 kilograms of toluene, and 20 kilograms of the product. But the real stuff here, the interesting part here, is that we already have minutes here. So we could either balance for hours, like if you want minutes, seconds, etc., we could do it. And not only that, if your, I don't know, your boss doesn't like international system units, he doesn't like kilos, he's like, what the hell is that? I don't understand you. Like most of clients will do, I assure you. Then you can change it to pounds. So what's the relationship between pounds and kilo? So 2.2 pounds, it's about 1 kilo. So just multiply that. You have 10 times 2.2. You will get 22 pounds of benzene, 22 pounds of toluene, 44 pounds of the product per minute, per minute, and per minute. So that's cool. Your boss will understand. It's the same amount, the same process. It's balanced. It's cool. Same product. And the other thing we could do, like if you're selling, this was with your boss, but you, I don't know, you were selling with other people and they don't like to work with minutes. They say, no, but we don't work with minutes. We have all our mass balances with hours. Like we work with hours and I feel more like I can compare my flows. Like say they use hours. Like they tell you I use 7,000 kilograms per hour. So you change it to hours and they will understand more than with minutes. So what do you need to change to hour is just the relationship. You already know 60 minutes is 1 hour. So just change, multiply by 60, it will be 10 times 60, 600, 600 here, and 1,200 here. Same product, composition doesn't change. If you don't believe me, you can check 600 times 600, you will get 1,200, and 600 divided 1,200 will give you half and half. So it's cool. This is what we're going to use in general. This is the basis of calculation and scaling up, because we haven't actually scaling up. We just are changing units, but scale up will be the same. Like they tell you, actually we did scale. It was here. This process was called scale up because we only had this 1 kilo and 1 kilo and 2 kilos, and we are now saying the same process, 10 kilos, 10 kilos, and 20 kilos with only one basis. The basis was 1 kilo of B. Our basis of calculation was 1 kilo of B, and scaling up to 10 was the process I call scale up. So good. The conclusion is that all processes must be and are balanced, and that's cool. And that's why they do a lot of pilot tests to see first if it works when it's small, and they try maybe a pilot one, like it's bigger, and finally they go big, like a super plant. Before it was, I don't know, 1 beaker, and then it was a tank of I don't know, some gallons, and now it's like a super tank of cubic meters. So that's cool. What I want you to show is when the process is balanced. So I give you some examples and when you can use or not. So you get used to know if you can solve it or not. You have here, first of all, here you don't have 100 kilos. You have 32 kilos here and 25 kilos here. So if you add up, you only get 57. And you know you have an inlet here. And if the process is steady, which it probably is, you need more data. Mass balance doesn't match, more data, or maybe actually you are accumulating stuff. So it's interesting to conclude there. Now, 15 moles here, 3 more kilos here, and 12 kilos here. Sorry, this one kilos. Yes, it is balanced. Even though we don't know the composition, you know you can balance it because you have kilos here, kilos here, and they actually match. Now, this is the interesting one. 15 moles, 3 moles, and 12 moles. You will say like, oh yeah, it's balanced because I have 15 moles and I have 3 moles here plus the 12 moles, which give me also 15 moles. So inlet and outlet of moles, it's okay. But it's impossible to know because you don't know the reaction. So this mole could be another mole, and moles are not balanced. You can only say kilograms entering equals kilogram out, because remember the example of A produces B. Sorry. You will have A lost and you will win B. So it doesn't make a lot of sense. So you should always ask, is there any reaction? Good. And finally, this is when 5 kilos, and you don't even have a kilo here, you don't have a flow, you don't have a composition. When you have this, you are almost sure that you have not enough data. And let's do an exercise. The next process needs to be scale up from 100 mole to 1250 pound mole per hour. So it's easy. We have this process here. We don't actually need to solve it. We just want to scale it up. And the factor that I'm going to use for scaling is simply the desired amount divided with the actual amount. The actual feed amount is 100 and the desired amount is 1,250 pounds per hour. So we have this factor. We just need to go and multiply each and each, and you will, like this will be the answer. You will have this answer. Look how this is different from this one here. You have 50 here, now you have 625, and I want you to see that the compositions here didn't actually change. Look, 0.6, 0.4, 0.6, 0.4, 0.95, 0.05, 0.95, 0.05. And these, of course, will also remain the same. And that was everything I wanted to show you for the scale-up and basis of calculation. Probably you haven't seen that much about basis of calculation, but don't worry. With the exercise, you're going to understand what is a basis of calculation. Scale-up is actually so easy. Just calculate how much times do you need to have a, I don't know, the factor, calculate the factor and just multiply, and you will know how much mass balance you will need for that quantity. What's up, guys? It's here, it's me, chemical engineering guy, and we're going to continue our course of mass balance. Right now, we're in the number 1, which means we are in the introduction, and we are in section 2, which is about how to account for mass balances. Now, we've seen scale up, we've seen type of processes, and we've seen a lot of system and theory about mass balancing. So you have no idea what I am talking about, just go back to the sections and you will find out what I am talking about. Because it's very important to understand all those topics, because I will be talking with you about that, and if you have no idea, then it makes no sense to be in this course. So please go backwards, learn it, and continue. So, mass balance for non-reactive systems. What does this mean is exactly what it says. It's a system that has no reactions. So, remembering we're studying steady state mass balances, which means no accumulation in the system. That's good. No reaction is involved, therefore there's no production nor consumption of matter, or well, not matter, species, and the mass balance generally goes as inlet equals outlet. Let me show you why. Now, as there is no reaction, there will be no production or consumption. Why? And because it is steady state, so there's no accumulation. Actually, it's zero, which is very, very nice, because we will have not to deal with these differential equations, etc. And let me show you mathematically how the equation gets into inlet equals outlet. So we had from the mass balance equation here, we have this, it's inlet minus outlet plus production minus consumption equals accumulation. So production, we have no production, we have no chemical reaction, and consumption, we also have no chemical reaction. Accumulation is zero by default because it's steady state, so we are left with only inlet minus outlet equals zero, which I like better to pass to the other side, so I can see that inlets are equal to outlets, which is obvious because if you get something inside and it's a steady state, you have no accumulation, it must go out. Now, this topic here is very important. For n substances in a non-reactive system, you can only make n equations. And what does n substances mean? It means that either we have water and ethanol, we have n equals 2. So what I want is to write mass balances. You know that you can always make a mass balance in the global section, which means in all the equipment. So if I had, I don't know, distillation unit and had feed equals vapor and liquid, the mass balance will be something like F equals P plus L. Now, that's one equation, equation number 1. But we could also do a mass balance equation based on water, which will be similar. X fraction of water in F plus times F. You also have the X fraction of water in volume and the vapor, sorry, and the X fraction in liquid. And not only that, we could also do it in the ethanol, which will be something like this. Okay, so we got another 2 equations to get a total of 3 equations. The problem here, guys, is that when you have 2 substances, you can only have 2 equations, because one equation will be dependent. What does dependent means? If you add these, you will get this. So either you get 1 and 2, or 2 or 3, or 3 and 1, but never use 3, because if you use 3, you will get to the elegant yet interesting solution in which you prove 1 equals 1. So right now maybe you don't understand that much, but what we have here is 3 equations and 2 unknowns. So the problem is either overstated or something is wrong. So now, just remember, we can write always in an n substance balance, we can write always an n plus 1 equations. So I bring you this problem so you understand what do I mean. Imagine we have 3 balances, 1, 2, and 3. Nice. And I want to solve for x and for q. So what I want is just 3 plus 1 equals q. That's number 4 equation. 3 equals x times q. Since I have q, I can substitute here, and I will get x. 3 equals 4 times x, which will be 3/4. And now I actually have all the values. I have x and q, the 2 unknowns I told you about, but I still have one equation. The logical thing will be either I substitute to be sure or stop. But if I'm looking for an extra value, this will not help. Look, because if we substitute 1 minus 3/4 times 4, this first parenthesis will give you 1/4, and the second one is 4. So 4 times 1/4 gives you 1, which is exactly the one I have here. So that's what I mean. You prove 1 equals 1, which is interesting yet not so useful. So guys, always do n balances for your n substance system. Anyways, let's continue with the next exercise. I will give you time to read it. I recommend you to read it before I read it. So I'll give you some seconds. So now, let's continue with our aqueous solution of sodium hydroxide, which is sodium and hydroxide here, which contains 20% by mass. So that's kind of strong. That's probably super alkali or basic. And because of that, we want to produce an 8%, only 8% solution by diluting with another stream of 20% solution of pure water. What else? Of the 20% solution with, okay, yeah. No, actually we have not, it's only water, pure water. Sorry guys. Now they ask me to calculate the ratio in liters per kilogram feed and the kilograms of solution per kilogram of solution in the feed. So let me show you the diagram so we get this problem straight. We have a feed, yes, but we don't know how much. We have a feed of water, we don't know how much we need to mix, but we do know it's pure and we know both compositions, that's good. And at the ending, you know you want this product, but you don't know how much. So we have to solve for this. What I recommend is first do a basis calculus, which is simply this one here. This is convenient because in letter C, you will see that they ask you what will be the Q for P. If P value is this one. So let's do it for this. I just write down here and let's go for A, B, and C. So let's do mass balances a lot. Global is inlet minus outlet plus production minus consumption equals A. I told you no production, no consumption, no accumulation. Then we have inlet equals outlets. And the first one is F plus water. The feed plus the water will give me the new product. That's good. Now, I have this other equation, which will be the mass balance for water. Look how I have always XWF. Let me read it for you. Is X means mass composition, W means mass composition of water, and F means mass composition of water in the feed. So you can only multiply by F, because this here, and this here, and this here, they are not the same. You cannot say it's one, or add them, blah, blah, blah. Whatever you want to do, you cannot do it. This one is different from this one, and this is different from this one. I use X only to denote composition. I use the letter W to denote water. And the third subscript, which is F, is to show the flow, which here is flow in the feed, flow in the water, and the flow in the product. So please make sure, guys, to understand this, because this is very, very important. You will not understand what I am doing with the variables. Now, I know I told you that if you have n substances, which is 2, you can only write 2 equations. But just for sake, we're going to write it just to be sure. Yeah, you can do it, because if not, there's no problem. But if you do it, you will always prove yourself that you're right. Because if you get to the conclusion that 2 equals 1, you're right. So something is right. So the same, X most mass composition of sodium hydroxide in F times F, and we continue the same with water, which this probably is 0, this will go out, but okay, let's continue it, and you will have the ending. So from this system, equation 1, 2, and 3, count all variables is F, W, P, which is here, we have 3 flows, XWF, XW double, XWP, we have 3, XW, and we have X sodium hydroxide F, sodium hydroxide W, sodium hydroxide P. So we add all, like, total variables in this system will be 9. We know some, we don't know another one, so don't worry. We will see that later. Now, let's account for every equation we know. We know the value of XWF, we know the value of X water P, and we know the value of XW, this should be water, so don't get confused. We have this value, and this value. Common sense, because 0, come on guys, I told you, there's no sodium hydroxide in the water, so ignore this, you know it's 0. So from here you have 6 knowns. Good. P, we established the basis, so it's okay. So we only need to look for F and water. Nice. We have a total of 9, and therefore we can say we have 9 unknown for 9 equations, which we can actually solve. So that's good. Now to finalize, or to give this to an ending, we substitute the equations in the mass balance, equation 1 and 2. We have this, okay, we just add the data. We have this number, we have this number, and we have these both numbers. 2 equations, 2 unknowns. Please, like 2 equations, because it's 3 and 4 equations. This one and this one. And 2 unknowns, because we only have F and W as unknown. Now, these guys is the only mass balance you need to do. Actually, all the next is only math, any guy that knows how to do some algebraics can answer this. Give this to any engineer, they will solve it so easily. Give them the whole problem, they will not solve it that easy. So continue, you get this equation, then you substitute this equation in number 4, you get an equation with only one, let's say one variable. Nice. Now it's time to get back. In past equation, we have two variables, we substitute one variable, we get one equation with one variable. And you get both that. Now, it doesn't mean that we're done, it means that we have all the mass balance or all the information needed. But we are asked to do kind of stuff. Because if you read A, let me go back, they ask you the grams of water per grams of solution in feed. So it's only F divided by W. You got F, yes, I got it. You got W, yes, you got it. So nice, we have did that. Now I'll get back, sorry. They ask you kilograms of solution, which is P, of kilograms of feed. So they produce it divided by the feed. We have P, yes, we actually give the number, and we have the F, which we calculated last. We got this. Good. And finally, well, actually we have no here, but they ask you how much water do we need. This is the water flow, is a direct answer. So that, guys, was one example of one mass balance in a non-reactive system. So hopefully you understood. If you have any doubts, you can send me mails or whatever. Please read the problem again, understand the problem, draw the problem with all variables and stuff, and then, more importantly, do the mass balances here. This, I think, is the most important part. Not this is just mathematics. You could actually upload this to a problem, and if you know all the equations, you will solve it. As I told you before, it's only math. So, thank you guys, keep watching, keep going good. You can go to the next video. See you there. What's up, guys? It's me, chemical engineering guy. I'm going to help you to solve these mass balance problems in this mass balance course. You've probably seen my videos before, hopefully. If not, please go back because you need to see them before understanding this video. Which is it possible to solve a mass balance here written? The problem shown is actually this problem. You want to read it, I think it's better just to see the diagram, but okay, let me explain it to you. 10 pound mole is being fed. It's being fed here, okay, that's good. And half is A, so of course the other half is B. They enter and then it is separated into streams. This one, letter D, flow D with 5 pound mole, and what else? We don't know C, that's why it's empty. And they tell you 20% of A goes to D and 30% of A goes to, actually this must be 80%. Because if 20% goes to A, the other percent must go to C. So we're good. This must be 80%, sorry guys. Now, all the variables in the problem, we must write them here. So you have the three flows, and the three substance fraction in each flow. So we have substance A, and we have three substance B in each flow. So So in total, you have 9 variables. If you don't believe me, count them. It's 1, 2, 3, 4, and 5. These technically could be changed to a composition variable, so that's why I'm not counting this variable for. So let's continue. Let's see which variables are explicitly given. We have f as a float, d as a float. We have x here, x here, x here. So the total we have 5. We will mark it as -5 because this will help us to know if we can solve it. From the equations, you know that 2 substances equal n equations. So n equals 2. We can do 2 mass balance, either 1 overall and 2 species or 2 species 1. I really like the overall and 1 species, so I just choose this. But you could say no, 0 and 2, whatever. The point is, with this, you can get -2 equations. Well, 2 equations that we will mark as -2. And then physical restrictions, you always know, hopefully, that from 1 equals x fraction plus y fraction in current in each flow. Flow F, C, and D. But we are giving 1, so we cannot use. So we're going to use 1. And finally, we have this quantity. That's why I didn't count it as a variable. I count it as a special, I don't know, like restriction. You know that C times XAC, let me go backwards. I'm telling you about this, you know this value, which is exactly C times X and C. So you have 2 variables which are being multiplied and give you a number. So you have a restriction here. So you have -5, -2, -2. You add these, you will get -9. So you have 9 unknowns or variables and you have 9 equations. You can solve this problem, and the only thing that can stop you now is math, because math will get you confused in the equations, blah blah blah. But if you are good in math and you understand the mass balance problems, you will have no problems. So let's continue. This science, it's called variable equation counting. We actually count the variables and we will count the equations. So with this, we will see if we can actually solve it. Don't just do problems, come on guys. You are engineers, or you're preparing to be engineers. You gotta analyze data, analyze what is the thing you need to do, what does the client wants, what does your boss want, what do you want to do in this problem. So first of all, read the problem, see what's given, and ask yourself, analyze the problem, see what can you do, what do you need, what do you expect, etc. If you just go and start writing equations, it makes no sense. That looks so like dumb, like I don't know what to do, but I'm just writing stuff. No, I recommend you guys, and this is for all the problems you're going to find in engineering. Don't just do the problem, analyze it. Now, many times you will not have sufficient data. For example, this one. You have one flow, and you know it's being stripped or divided into M2 and M4. M2 passes directly to this and goes as M3. So probably you know the mass balance will be M1 equals M2, or M1 equals M3 plus M4, depending on what subsystem do you get. You get only this system, or if you get the whole system. Anyways, guys, you have only 2 equations. Okay, you know this value, but you don't know how much to M2 or M3 or M4 are. So you have a lot of unknowns and only one variable, one equation, two equations, so you will not be able to solve it. So look at me, guys. I just wrote like stupid. I just wrote m1 equals m2, m1, before even analyzing if I can do it. I show you guys, like, if you tell like someone that does not studies engineering, you show it this, they will tell you, hey, come on, guy, how can you do? You're not telling me how they are being split. How can I do it? But if you just go write equations and look and try to solve, this will not help. So we have a lot of that discussion, try analyzing, but now it's time to relate variables and equations. How can we get equations? Well, you can get equations from mass balance. Mass balance, either global, species, whatever. But you're going to get only n equations, remembering that n is the number of substances. So actually you only got one substance, you either do the mass balance of the total or global and the mass balance of the substance. And please do this exercise, guys. You will see that it's the same. That's why you don't do it, because if I tell you 1 kilo of salt goes out, either I do the global will be 1 kilo enters, 1 kilo goes out, and if I do the balance in salt, I will say 1 kilo of salt enters, 1 kilo of salt goes out. So that's why it's the same equation, guys. So that's why we only have one independent equation. We could have two equations, yes, of course, but one will not work. So pay attention on that, guys. Now this one, guys, is tricky because energy balance, we're not going to see this in this section or in this course. This is not included, so just have it as a reminder that if you have energy balance, you could, in theory, relate your mass balance and get a complete mass balance. You will see this in the energy balance course, so don't worry. Also, from the problem in the text, or when the problem is being like narrated, you can see a lot of like important data. For example, product is 1/2 of the feed, or 30 kilograms of A are in the stream B, or the L and B ratio is 0.55. The final amount of F in C is the same as A. All this stuff that you maybe see as a sentence are mathematical equations. You just need to relate the variables. Another one, physical properties, law, and data. Densities, you may not have it, but you can look at the internet, Google, whatever, Wikipedia has a note, databases, you name it. It will relate volume to mass and mass to volumes, etc. With molecular weights also the same, guys. Specific gravity, same history. Okay. Gauss law. We're going to see this in chapter 5, which is the next chapter. We're actually introduction. We are going to see this in MB2 if you have a doubt. But right now, we don't care. You could actually, from the ideal gas law or the real gas equations, relate temperature and pressure to eventually moles of the gas, and from moles you can do mass. So that's good also. And phases. Phases, we will going to study this. This is actually chapter 6 in your Richard Felder book. We're going to see this in mass balance 3. We're actually in mass balance 1. When you finish mass balance 1, so we're going to see the ideal gases and that in mass balance 2, and finally we see phases in mass balance 3. you will relate X and Y compositions. X is generally for liquid, Y is generally for vapor, P is pressure, T is temperature. So you can relate either of these to get one. You don't know this, but you have this, okay, you can solve it. Actually, I put it here, chapter 6. And finally, physical restrictions. Like the most typical we're going to find is this. That you always need to finish with 1. 1 if you know x, but you know it's 0.6. This is technically no known because you already know this equation and you could relate this one. So I'm going to use a lot of this. Sometimes you're going to see a flow. I will tell you x. And instead of using y, I will use 1 minus x. Because it is only a binary compound. Or even larger, like if I have x and I have 1 minus x, and probably if I have 0.3, I will have to add that one, minus 0.3. So I think you got the variable equation where to get variables. You have remember mass balance, energy balance. From the problem, you will get a lot. Physical properties, law and data, and then physical restriction. So we need always to find these unknown variables must be at least equal to the independent equation. The hard part is not getting the variables. Actually, variables always are being looked for. The different or difficult part is the independent equation. This is actually what is difficult and what most students struggle to get. So keep attention. So of course, we're going to try to decrease the number of unknowns. So if I told you I got this problem with 10 unknowns, I will be like, whoa, guy, what up? Let me see and try to get less like variables, relate variables. As I told you before, if you got y, we could use 1 minus x. You have a binary system here. You could use this and then it drops by 1 and keep doing that. Maybe you get, I don't know, 5 variables and you got only 4 equations. Now you just need to look for 1 instead of 6. So the tip here is to search a lot. You need to always be looking which equations, which variables relate, where can you get more info, etc. That's the trick. Actually, you cannot learn it. You need to practice. And finally, I bring you a variable equation counting exercise. I've got this one. Feed goes in. We don't know the feed. We don't know the composition, but we do know the final composition and the final flow. So let's do it. Variables, all feeds here. Because actually this is a volumetric one. We do not have a massive one. So that's why I put a variable here. Now, all compositions in F, I don't know it. All compositions in, where is it? D, I do know it. No, actually, yes, I do know that. And the composition in water, by common sense, I have it. I have 12 variables. Good. Now let's solve it. From node 1, I'm going to add this node, is 95% of the vapor in feed. So the vapor goes something about a relationship 95%. You could get this here. It's the water. They tell you 95% of vapor in feed condenses. So all the vapor here will be 95% of the feed. Let me get it straight. We have water here. Yes. 95 this water will condense here. So 95% of the water in feed is exactly the water that condenses. So we got this new equation. Cool, huh? And 5% of course will go to D. This is dependent, you know guys, because you know the relationship of 1 minus x. You think it's a new one, but actually it will not help. But I do put it here just if you have curiosity. And now from another note, you can relate mass with density. And another thing I want to denote is a relationship in air. Normally in air you have 3.76 nitrogen moles per each mole of oxygen. So let's do our degree of freedom analysis. Have -3 mass balances because there are 3 substances, -3 variables that we don't have, which are these. No, sorry, these can. We don't have these 3 variables. No, sorry, variables given. We only have these 3. And from node 1 we can check one equation, and from the relationship oxygen and nitrogen you get another one. So 12 variables minus 8, you will get to use that. You have no data enough to solve it. The degrees of freedom is equal to 4. You are able to solve one problem when the degrees of freedom equals 0. So we will need either 4 data or 4 equations that relate all variables before. Hope you understood. Try to do this problem. You will be sure that you cannot do it. You will get frustrated. You will try a lot, but with this small analysis, just to see how many variables I have, how many equations can we get, I'm knowing I will not be able to solve this. So thank you guys. Keep watching and hope you're learning. What's up, people? It's me again, chemical engineering guy. I'm going to help you pass through the mass balance course. We're right now in the introduction and we are going to see the general mass balance approach to problem solving. What does that mean? We're going to do mass balances, you know it. Hopefully, if you don't have any idea of what I am talking about, please go through the previous lessons and videos. Because if not, you're not going to have any idea and you will not understand this. So, in general, we're going to solve mass balances. So this is like a methodology or just follow through idea you can use so you get easier and simpler processes to solve it. Number 1, of course you need to read it first. That will be number 1. Or number 0, you read it. You have a problem. Now you have a problem. How do you do it? First of all, draw flows, streams, equipment, units, everything you think it's important, draw it. And of course label it, because if you don't label, it's very difficult to relate variables. In this block diagram, of course. Now, choose a convenient basis of calculation if not given. They tell you base it on a 100 kilograms per hour production of P. Well, then use this as basis. You have nothing, use, I don't know, normally 100 kilo will be good because 100 give you 100%, I don't know. You can use infinity amounts depending on the case, and you will see a lot in the problems I show you. in the problem section, you will see a lot of basis of calculation, how to choose it and why. Now, tag all the variables in the diagram. Don't let any flow, concentration, temperature, pressure, equipment go by. If you don't know this, like label it, please. Now, you have all the data, you have all the variables you need, and of course, I tell you before, analyze the problem. You need to think before actually doing the equations. Think, what do you need? What do you will require? What are the equations? Can we solve it right now? We need more data. I need to look for densities. I need to go internet and check some stuff. I don't know. Do your analysis of variables and equations and do a degree of freedom analysis, which is essentially counting variables versus counting equations. If it's solvable, please continue. Change all volume data to mass and mole because volume is not constant. We have no volume principle of how to say, you cannot destroy and construct volume, you can produce it. We have not that. We have mass and mole. So please change all to mass and mole if you can. So when data is given, change all either to mass or mole. I would recommend to work with mass in certain cases. I would recommend to work with moles in certain cases. This will be in general where there's a reaction, and with mass when there is no reaction. But that's me, guys. You can actually work with either of both. You will be converting a lot, yes. But if you feel you have a better chance with mass rather than mole, do it. And this is the most important one, I think, because translate all text to equation, that's an art. You need to understand, you need to relate to say 1/2 of F equals C. This will be read as 1/2 of the feed, or they will tell you like the product is 1/2 of the feed. That is the art of translating words into equations. And you know why do we need equations? Because we need to look equations to get variables. So you will need that. Now, after all, just do and write mass balance. Now that you know you can do it, I recommend you to write every mass balance. You probably know that you will not use one, as I tell you, n equations for n substance. But just do it for the sake of having everything perfect, everything written, every mass balance you will write, etc. Good tip is to order from number of variables to from a little. For example, you have 1, 2 to a equation that has, I don't know, 3, 4. And finally, which is the best thing if you are good in math, just do the math. Solve all equations and variables. You will get all the variables, and once you have all variables, you will have all the flows, all compositions, etc. Now, 10 has more to do what you are requested to rather than what are you going to calculate. Be sure to scale up. Many times, many students just finish, they got these like, they solve the equations and variables, but they don't even know what they're asking. If they tell you the relationship between F and C, and you just calculate F and C, well, come on guys, just do this division and you will get it. Because if not, it's okay, you got the data, but you didn't answer what I was asking, which was the relationship. Make sure also to scale up. If they tell you, okay, scale this process to 100 kilos, and the process was based, your basis of calculus was 1 kilo, that's so easy to multiply by 100, just do it. This all depends according to the problem statements. So you gotta check, when you got all the data, go always check back what are you asked for and do an answer for it. So, have here one example. Please read it. I recommend you. I'm going to make a pause as well so you can read it. Now, a distillation column is being fed by a stream of 45% benzene. Okay. And the balance is to length, which is rapidly 55%. If you don't believe me, calculate it. The product D flow contains 95% of the benzene. This does not mean this is not composition. They are telling you the 95% of this benzene is in the product D. 8% of the fed of benzene is being produced in the bottoms. Okay, we have more data. If feed F flow is 2,000 kilograms per hour, determine the flow in D, the mass flow in benzene, and toluene in the bottoms. So technically they're asking everything. The flow in D and the flow in the bottoms, and not only that, they want to know how much benzene and toluene. So you need the compositions as well. So you gotta work a lot. I bring you this example. Hopefully you understand it. It's number one, I told you before, draw and label. Draw your diagram, here I draw the stream entering, I have this data, I put it in, and I know it's 0.35. I could write this, it's easy, because why do you do this like as a complicated calculation when it is so easy? So write it. You have your unit operation block, which is the distillation. Yeah, you could use a tower, whatever you want. You have this flow, which is the vapor ones, which is D, and you have this flow, which is the bottoms. You know this is 0.45 of benzene here. This is not composition, is 95% of the initial benzene. And I write generally nodes that cannot be like introduced in the diagram. Look, node 1 is 8% of the benzene in 2, which I think is this. In feed is the equivalent to benzene in B. And node 2, I know that B times XB in benzene will give me the amount of total benzene that I am requested for to calculate. And B, which is bottom, times the molar composition or mass composition of toluene in bottoms, which is this one, will give you the toluene, which I'm asked for. So good. Now it's time to choose a basis of calculation. Use the problem feed, why not? We could use 100 and we will need to divide, and then at the end of the problem we will have also to multiply, but why not use 200 from the beginning? Good. It's not that you have to, but it will make it easy. Number 3, tag all variables. In F you get XBF, XTF. B means benzene and T means toluene. F means in F. D means in distillate and B means in bottoms. So this is kind of tricky because it's mass fraction of benzene in bottoms. So this is tricky, guys. Put attention in this. Pay attention, please. And good, I just like circled this because these are variables that I invented myself. This is for letter B. They asked me the amount of benzene and toluene in this flow. Here they are. Now, number 4, count all variables and equation before actually solving. So I got 3 flows and 6 compositions, a total of 9. Good. I got 2 equations in the mass balance. I got 5 implicit equations, which is one for composition and one flow. I got one 8% ratio equation that I can relate. And finally, I got one restriction in the composition. So thankfully, I got 9. Since the number of equations is the number of variables, I can solve it. So let's do it. Now, let's convert all volumetric flows, sorry about this, volumetric flows to mass flows and mole flows. So thanks God in this problem we don't have nothing about that, so we don't need it. Convert all data, mass, moles, mass flow, molar flow, to either mass or mole. We don't need it because everything is in mass. And number 7, let's translate all the text to equations. So from node 1, you know 8% is something. So we read 8% of the feed of benzene. So this is already benzene in the feed, benzene in feed. And they tell you that 8% of this benzene in the feed is the benzene going in the bottoms. This is benzene going in bottoms. So now again, I want to repeat it. This is benzene in the feed, or being fed. So that's why here is X and F, because to get the amount of benzene in F. But they tell you that only 8% goes to the bottom. So you got this new equation, which could be also the same as to say 92%, also the other percent, goes to the distillate, wherever you want. Now, write mass balance equations. Mass balance in global and mass balance in one species. You could do the other one, but they will only, number 3 and 4 are the ones that are going to work for you. They're going to give you the values you're looking for. So simply from the balance, you know, you have this. You have inlet is F, outlet is T and B. So just solve it and you have this. Now, mass balance in benzene will be the same, just add the fraction here, and fraction here. Good. Now do the math. You have everything to do, so just substitute. I substitute F here. Here goes F. You got this value, yes, in the distillate, so it's okay. And you know that this is what I'm asked for. And what else? Okay, another time. F, this data, you have it. So from here, just to let you know, we have this value too. It's here. And XBB is the thing I'm looking for. So actually this is, I think I use C. So we have 3 equations and 3 variables. I don't have D, I don't have B, and I don't have BXBB. So let's continue. We can solve it. And from D, this one is that one here. I'm solving, and then I get D, which will be probably that one here. Yeah. No, or here. So we get D. From D, we go to substitute this in number 3, which is this one. It's very, very easy. 2000 equals this flow. Just find B, and you find B. And from 1, which is this one over here, you just need to substitute all the data that you have. You will get 72. But you're looking actually for XP. So 72 in the total gives you this percent. Nice. Now, we in the first one, letter A, we are asked for the distillate. Distillate, we have it as a direct variable, good. And in the second one, we are asked for the benzene in the bottoms, which is XB, or the fraction of benzene in the bottoms. We have both values, which is actually C. Go back. It's where is the value? XB is this one. Look how they relate. So we just answer the problem or solve it. The conclusion: if you follow the methodology I showed you before, it helps. Of course, you need to learn it, but it's also common sense, so don't worry. The difficult part I told you before is the assumption of equations, variables, data, how to relate them, and essentially that. Mass balance are easy if data is known. The more data you know, the easier it becomes. So if you need more exercise and problems about the mass balance with no reaction, mass balance of 1 unit with no reaction, or degree of freedom analysis, or whatever, probably I have it there in my course. Go to this web page, which will be available. Go to the section of courses, choose mass balance course, and go to the problem section. You will find the problem index there, which probably you will like, because you will choose, I want to practice mass balance in no reaction. And you click it and you get them. So that was everything I was going to do in this video. Keep going because it's not over. We still have more to do. We are only like in the 30% of our class, so just keep going. What's up, guys? It's here, it's me, your chemical engineering guy. I'm going to give you this lesson about how to account for 2 units in a mass balance. You have no idea what I'm talking about, or if you missed the mass balance in 1 unit, you gotta check my previous videos because probably you will get it way better. So if you already see them or saw them, you can continue. If not, go backwards, please. What are we going to do in this mass balance in 2 units? When I say units, I am referring to process units or to unit operation unit. For example, these distillation columns. Because in chemical processes, it's so normal to have more than 1 unit. So 1 unit is nice, you can have it, but the most normal thing is to have at least more than two or more. So we're going to do a mass balance in 2 units, and later we're going to do a mass balance with more units. So let's continue. We could do a global balance in the whole system, which will be the entrance of this sour gas and the entrance of this makeup water. There's an exit of sweet gas, there's an exit of acid gas, and yeah, I think that's everything. So in general, in this huge system, what you are doing essentially is you're feeding sour gas with makeup water to get sweet gas, which is actually just gas with no acid, and the acid gas. So that's cool. Now, we could create subsystems. So if you understand the part of systems and subsystems in process, I think I showed them in mass balance 1. It is the part in which I talk about theory. You will understand that you can have sub-processes inside the same process. And it's the same here, guys. You can have systems inside the systems. So before our system was all this. But now we can have subsystems. Actually, you could have any subsystem. But the ones I'm going to take care about is this one here, the distillation column 1, and this one here, the destination column 2. This I could also make mass balance, but I'm not going to do it because these are just like storages, containers. So there's no interest. The interesting part here is to see how the sweet gas goes here and the acid gas. So remember, from the mass balance, you can create a mass balance equation, inlet equals outlet. So continuing, I just like a remember, subsystem is any portion of a chemical process. You could have a system that has many subsystems. In the example could be unit operation, as it was the distillation column. You could actually make one subsystem. You have, I don't know, two distillation column, and then you have another one here. You could do this mass balance, and this will be a subsystem. A subsystem that counts with two systems and general system, of course. You could also have a mixer, like here, two streams meeting one point and then they go out. And what else? You could also have a splitter, two currents meet in one point and they split. No, actually, sorry. One current comes here and splits up and down. You could do this, take it as a unit, because actually when you see in mass balance they just connect like this, it's not magic. You have something there. Even this, the most basic mixture is something like this different. You have this pipe, the pipe comes here and you mix them. Okay, now we need to apply to different subsystems, so we could find more independent equations. Remember guys, we want equations to find variables, and hopefully these equations are independent, because if they're not independent they don't work. So make sure they are independent. And why do I say that? Let me explain it. For example, you can find many equations and many of them will be redundant. What does that mean? That they don't tell you actually something new. They are masked or they are hidden, but they tell you nothing. For the other part, we can have dependent equations that tell you something new, something useful, and you can get the variable in general. So these ones are the one we want. An example of a redundant equation, I bring you this simple mass balance. It's 2 unit, A flow, B flow, C flow, unit 1, unit 2. And of course, we could do mass balance in the unit 1, which will be this one. It's A equals B. It's easy to do. Then in the mass balance of the system here, number 2 is B equals C. Also easy. Of course, we could also do the normal mass balance of the whole system, which will be A equals C. So now we got three equations, but what I want you to tell you is this. Number 1 and number 2 will give you number 3, because A equals B and at the same time B equals C, so you can say A equals C. And therefore this equation that sounds good, like, oh my god, I have another equation, doesn't actually give you something new. So it's not useful. Sorry guys. And please make sure, especially while doing this type of balances, when you have many units, make sure they are independent. bring you here one exercise, 2-unit process, simple. They tell you, okay, they show you the chart is here. Steady state of 2-unit operation is shown below. H blah blah blah. Actually, you can pause the video if you want, read it, and I will read it for you. Now, each stream contains 2 components, A and B, which I have here, and 3 streams whose flows, rates, and or composition are not known. And they are labeled as 1 and 2 and 3, but I labeled them this flow, this flow, and this flow is not known. And also these compositions are not known. But everything else, we know it. They kindly ask you to calculate the unknown flow rates and composition of stream C1, C2, and P. Perfect. The first thing we want to do is analyze the data. Just watch the diagram. What I like to do in general is just do a general mass balance. Like to see what enters, what goes out, what leaves here, etc. And as you can see, F enters, gas 1 goes out, X enters, gas 2 goes out, product goes out. But more interesting is that we have this value, we have this other value, this other value, and we only miss this one. So just by watching, I already know I can get P. And actually is what I am going to check, go for P. Why? Just because I told you so before. It's easy. You could check another stuff, yes, but the most recommendable to do is the mass balance in a global scale. So mass balance in global system will be F goes in, X goes in, G1, G2, and P go out. So remember, we have this mass balance. It's okay, it's fine. So we get F plus X equal G1 plus G2 plus P. Just substitute all the values, guys, here, and you will find an equation with only one variable. So we can solve it. This is it. P equals 130 minus 70, and you get the first value of P. I already told you, I highly recommend to always start with the overall mass balance, if possible, of course. If it is not possible, for example, you didn't have this and this, well, doesn't make that much sense. But still, you can do it to have an idea. Now we go here, calculate stream C1 and C2. That's very easy. We go to the mass balance in the mixer. Remember the mixer, it's here. Maybe you don't think it's a unit or so, but it is an actual unit. So please take care as it were a unit. So we got C1 enters, X enters, and C2 goes out, which is mathematically shown here. Good, we have equation number 4. Now let's do the mass balance in unit 2. Why unit 2? You could also make mass balance in unit 1, but I choose 2, I don't know why. I prefer it to refer to P rather than to refer to fit, because P is the new one. Anyways, mathematically entering one, it's C2, and going out is G2 plus P. So we got 2 equations with 2 variables, which is C1 and C2. We could theoretically solve. So let's try it. I'm going to try, yes, this equation, I put it in here, And then I just substitute values 30, 60, and minus 30. You get 60, which is the first value of C1. And we have the value, just go back and substitute it here back. 60 plus 30, you get 9. So easy. So using these two equations, we got C1 and C2. So now, given P, we would like to calculate other flows. If it is not possible, you need to find another composition or etc. But right now we could do a balance in mixture, a balance in the unit. If not, we will have to do a mass balance of, I don't know, A and mass balance of B, etc. So this time we were lucky, it's easy one. Now, the mass balance in the units. We want all compositions. Actually, we just miss one, C2 and P compositions. So we could either use this system or this one. I think I'm using this one here. So I'm going to do the mass balance in the global scale. Why global? Because I think global has less problems, because here I calculated this and calculated this, so it's too much calculation. Maybe I made a mistake. I rather prefer to know I only made a mistake here. But mathematically, it's the same in theory. I'm just telling it because me, or I as a student or as an engineer, I would rather do this than this here, because this is more probably to get an error. But anyways, let's continue. We have the mass balance in global, and we have mass balance in the global system, but over A. So we just simply check x of A in feed, x of A in x of A in gas 1, x of A in gas 2, x of A in XAP, and yeah, just substitute all the values. We have all these, yes. 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 Do we have this? Nope, we don't have this. This one, no. And we have P, just calculated, which is actually here. Oh, sorry. We don't have this, we have P. So this is 50, this is 30, this is 10, this is 36, 18, etc. We have one equation with one variable. We solve for XAAP, which is the mass fraction of A in the product stream. It gives you 0.1. Nice. We just know either we could go and make another balance equation, a mass balance global over B, or simply use this because we know that it's a binary component. They have two, which is A and B, and they must add 1. So if I know A is 0.1, XAB, of course, it will be the difference, which is 0.9. Nice. Given all flows calculated, we only need to find all compositions. We already done it. Check mark. Fine. We have all compositions, I think. Oh no, actually, we just calculated the compositions in P. Sorry, guys. Let's continue. We need to find the compositions in C and C2. So let's go. C1 and C2 compositions. We're going to do a mass balance in unit 1. General one is the feed enters and separates in gas 1 and C1. We do exactly the same as we did in the product stream. You know XAF, XA gas 1, XA gas no C1. We have all this data, and we just calculate C1. So the only missing is this. We solve for XAC and we get 46. And using the same correlationship of 1 equals XAC1 plus BC1, we get that the difference is only 1 minus 46.46. You get 0.54. Good. We have C1 composition, check. Now let's go for C2 composition. Let's make a mass balance in general, and we get this. We could also either do it here at the end or before. I prefer the end, so let's do it. Finally, we do a mass balance in unit 2 over A. That is exactly XAC, XAG, and XAP. We have C2, we have gas 2, and we have P. We just need to find the composition of XAC2, which is only one equation right here, and just solve for XAC2, which is the composition of A in current or stream 2. It's here. You get the value of 0.26, and you know that the difference must be 1. This is not F, it's 1 equals XAC2 plus XBC2. So I've got this, I've got 1, you have another equation just as before, and we get the composition in C2. So perfect, we have the composition in P. Now let me just tell you how we did it. We got P first, we got then C1, we got then the flow in C2, and having these, we made mass balances to get the compositions X, A, and B by doing mass balances of species. Good. So just to conclude, to tell you how it was done, start doing overall mass balance. It doesn't have to be like that, but it helps a lot. Try to get all the flows first. I told you we got P, C1, and C2 first, but you don't have to. You could actually go directly to calculate compositions, but it will be much harder. And then calculate compositions by doing mass balance in the units. Mass balance, I mean global and by species, in this case A and B. So good, guys. Hopefully, I think, yeah. Next topic will be more units. This was only 2 units. Hopefully you understood. If you didn't understand it that much, probably either repass or reread this problem or go to the mass balance of 1 unit. I think it's so clear. The difficult part comes here when there's many columns, but no, sorry, many unit operations. But in general, don't worry, it's easy. It's just mathematics. Just try to do the equations. The only problem is to get the equations. So see you in the next video. What's up, guys? It's me again, chemical engineering guy. We've seen before mass balances in 1 unit and mass balance in 2 units. All these with no reaction. Now it's time to do a mass balance in a 2 plus. What does that mean? 3 or more units with also no reaction. And the first thing you will think, of course, it is more complex because you have, for example, 1 unit here, you have 1 unit here, other unit here, 1 unit here, units everywhere. So that's not that good for the complexity, but you can account them by equations, relationship, everything. So don't worry. Now, the mass balance or the subjects you can do, like you can do either global, you could choose 1 unit, or you could choose a group of units. That is what actually makes it complicated, because I can tell you that the fuel goes in, and I don't know, I do all this mass balance, have inlet of waste acid, inlet, fuel as inlet, and water as inlet. As outlet, exhaust gas, regenerated acid, ferric oxide, etc. So this is the easiest one. So just let me, sorry guys. Again, this is the easiest one, the general mass balance, but we could also do, I don't know, a mass balance. They could tell you, okay, the acid enters the separator is, I don't know, 100 moles, and it is 5% of the one that exits this stream. So you need to do the mass balance in here. Or it could also happen that they tell you, like, no, first you got to do this mass balance here, and then you can solve this mass balance here, and then you will be able to do the general mass balance. So that's the problem. The problem is not that we don't know how does it work. The problem is, where do we start? Which mass balances do we do? Shall we do the global balance, a unit balance, a group of unit balance? Who knows? You need to analyze the data, see what do you need, what data do you have, which variables do you care about, which is important, which is not, etc. So let's go and treat one of these. This is actually pretty easy. It comes in chapter 4 of the book of Felder, Elementary Principles in Chemical Calculation, I think it's the name. And no, let me check this. Elemental Principles of Chemical Processes. So if you check this problem, you have one unit here, you have two units here. Actually, this counts also as a unit because it's a mixer. You have 3 units. And finally, you have this separator. You have 4 units. Now, they tell you have this flow inside, inlet goes inside. And you have P as a product, and the outlet of each unit will mix. And we will treat it to separate into B vapor and B bottoms. They tell you, please calculate flows E1, E2, R, ET, not the alien, B, and B. Good. And if it wasn't enough, they tell you, please calculate each composition. So this is going to be a lot of work. But what you will see in the example is that from the previous example or problem, it is impossible to calculate all flows because we need more data. We need either explicit data, more compositions, more flow values. We need relationship. Maybe if they don't give you explicit data, they will need to give you a lot of relationships, a lot of ratios between flows. They might give you percent of mass of flows. They may also give you other type of data which could be written mathematically. So you need to be creative and always think more. And as I told you way before in one video, I think 3 videos ago, you need to analyze. If you don't analyze this problem, you will be doing mass balance everywhere. Mass balance here, and mass balance here, and mass balance here. You got 4 units. Now, a mass balance here, a mass balance here, and a mass balance here. Not good. And a mass balance here, and the global. So you will have Actually, how many circles? I don't even know. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 mass balances in total, and just be writing equations. No, guys, you gotta do the analyzing. Just check the variables, check the equations, number of equations, and solve. If you can do it. If you cannot do it, you will need to find more explicit data or relationships or everything. You need more data. So if you need more problems, please feel free to go to this my webpage, Chemical Engineering Guy. You will find a section in the courses. Just click courses. You will see mass balance course, and there's a problem section in which you will find a lot of problems. I think I have like 40 problems in general in this section for chapter 4 of Felder, chapter 4. All these pair problems that come in the book, I solve them for you. So if you need more help, more problems, more exercise to practice, go here. You will find an appendix and you will be happy because you just click in 2 plus units or 2 units or only 1 unit, etc. So that was for the mass balance in more than 2 units. Let's continue what is going next. In theory, recycle and bypass. See you in the another video.
Excuse me, sir. Tapos na yung video, sir. Excuse me, sir. Sir. Tapos na yung video, sir.
Sorry guys ha, naghang ang akong kuan. Kadiyot lang. Wait kadiyot ha.
Okay.
Kaganiya pa na ako gikuan, di man ma-operate na ako. Galisod ko pagkuan. Ay, unsan man ka? Oy. Ayan nga lang. Okay, we'll just cut this one, no? Di na ako ma-recover. Okay, sorry for that, guys. Doon na pa duha ka videos unta, no? Pero sayang, no? Dili na makuha na ako. Medyo na taot siguro. Kaganiha pa na ako gi-operate. Okay, so anyway, ang point nato din yung objective is for you to know how to balance the mass, no? In different system, no? Then I one system, two systems, and multiple systems because designing reactors involves mass balance. Then we will go to the mole balance, no? Which is ugma na na. So kinahanglan nato nga we are going to finish the mole balance in one take lang. So hopefully we can do that by tomorrow, no? Sa tomorrow is Friday, so hopefully mabuhat na to na. So for the meantime, we are going to have an assignment for the mass balance. Hello, madungog ko? Madungog ba ko dili?
Excuse me, sir.
Yes.
Magklase ugma, sir, nga holiday.
Holiday mo di ugma, no? Sorry
Yes, sir.
Ay, samot nagkadilidaan ni. So we don't have a class. So sige, ang ato na lang mole balance sa Tuesday na lang ta mag-discuss sa mole balance because definitely we'll have a quiz on Friday. Kaya kinahanglan ta at least two or three quizzes for midterms, 2 or 3 assignments, and then midterm examination. Okay? So ako lang advice guys because you should be lisod ta maghataw og assignment sa online, no? Kay dali ra kay nato ma-search sa internet, no? Anyway, I will not be restricting you for that, no? Only you are going to do the internet or the research in internet as a guide, no? You are going to solve it by yourself first, no? Klarohon sa ninyo, okay? So that's the best way for you to learn, no? Okay, then after that, you can correct it, no? And then submit it, no? It's okay for me, no? For as long as you did it your best, no? Inyo sa nang gisolve and then compare your answer to the solution sa internet. Okay? So makita man nyo na that's why ang assignment nato nga dili ko strict assignment because it takes 2 or 3 days for you to finish that one. So but the point there is that you are going to solve the problem first by yourself, no? So dili kay diretso na mo copy sa kuan without usik-usik lang ta sa kwarta na, no? Dili nothing what time na katunan na niya, okay? So lahi man gud nata sa face to face kay diretso ta makakuan dayon nya ang ato ang kuan diretso lang, no? Ang ato ang hindi nang makasave tag time, no? Kay shortcut naman lang, di naman tayo ingon ani nga moagi ta og kanang mga videos magkuan sus kapoy kaayo lisod kaayo, no? Stressful on your part as well as on the instructors, okay? So we will have a quiz definitely by Monday, and then assignment also. Okay? So that will be all for the mass balance. Ako na lang i-upload ang nag-error nga 2 videos, no? Ganihara ko ga di gyud mo ko ano, ultimo akong microphone dili nikalit lang siya og ka kuan siya. Di ko kasabot og ngano to. Okay? So please open your microphone for the final attendance. What time is it? Sakto naman po di ay. Abarkis,
Present.
Abrasaldo,
Present, sir.
Anchita,
Present, sir.
Arong,
Present, sir.
Varius,
Various present, sir.
Elbistre,
Present, sir.
Kanyite.
Present, sir.
Nalit ka, ganiha Kanyite.
Mga kuan na po kasulod, sir. Mga 3:40.
Siya, nag-start ta murag mga 3:30 man. Sige. Wait. Caballero,
Present, sir.
Casañares. Casañares, nawaha man si Casañares. Clemente,
Present, sir.
kisa man nun to? Casañares. Ano? Koyos.
Kuyos,
Present, sir.
Kisa man ang usa, nasapaw. Si Clemente to?
Yes, sir. Castañares, sir.
Casañares na. Sige.
Yes, sir. Nawa ang connection.
Okay ra. Koyos Dakay.
Present, sir. Present.
Inglasa.
Present, sir.
Dinopol. Jade.
Present, sir.
Durham.
Present, sir.
Nalit ka ganiha Durham?
Oh, sir, kay connecting ko mga 44 ko nakasud.
Sige. Scario Jan.
Present, sir.
Ricky.
Sir.
Kirua.
Present.
Ilina.
Present, sir.
Jarina.
Present, sir.
Agroma.
Present, sir.
Leopando.
Present.
Luwab.
Present, sir.
Lumibaw.
Present, sir.
Yuli. Wajud si Muli.
Present,
Murok.
Muli, sir.
Diyan. Nag-chat mo dito siya, no? Sorry.
Oh, sir. Ganun.
Yep. Sorry. Murok.
Morok, present, sir.
Kanang manok. Murag kang muli ng manok. Nerbida.
Present, sir.
Alice.
Present, sir.
Pipito. Pipito. Diyan mo siya ganiha. Perez.
Present, sir.
Randas.
Present, sir.
Ponte.
Present, sir. Reponte.
Robin.
Present, sir.
Sanoy. Kisara.
Sanoy, sir.
Present.
Sanoy, present. Karon kisa tong usa. Nasod. Sinilio.
Si Pepito tong usa, sir,
Present, sir.
katong
Sinilio.
karat.
Nasipito. Sige. Sinilio na ano?
Present, sir. Sinilio.
Suson.
Present, sir. Susan.
Nalit. Kung sa oras na nakasod, Suson.
Mga 4 na jud ko kapin na jud to, sir.
Late ka. Toledo.
Present, sir. Si Pipito, sir. Present.
Ako nang gitangtang. Vergara.
Present, sir.
Yaon.
Present, sir.
Okay. So, that's it guys. Ang duha ka video, I think duha or tulo ba to ka video pang kuha na gyud, di na gyud makuan kung saan ako og maniobra, no? And then, asa pa akong microphone, nawa mo kalitang ko ang good internet sa PLDT, and then akong gibalin sa phone, no? Gihimo na akong modem ang phone. Mao to siyang nawa, di na jud nun makakuan. So, nibalik na siya dihang akong tangtang ang kuan sa phone modem. Okay? So, we will have our first quiz by Monday, so we will not be meeting. Adto na ko ibutang sa Moodle, no? Okay? And mag-upload po ko og assignment na to. Katong naa sa tong PowerPoint nga wa na to gi-discuss, no? Ato dito ang assignment. Okay? So that's it guys. If you have no questions, you can log out now. God bless.
Excuse me, sir.
Yes.
Kanang mag-ask lang kami, sir, ba ang exam ni Monday kay terms ra ba daw or naa ba daw calculations ra jud siya?
Ang quiz na to kuan siya, short answer quiz o multiple choice. At the same time doon na siya computation. Bali mag-choice ka sa answer o single answer. So in other words, real time siya. Okay, so dili ta mag quiz nga ang atong assignment mao problem solving. Pero ang quiz real time man siya, so doon na tayo multiple choice. So kung maigo na to og problem solving, tagaan mo possible answer. Okay? Then doon na po tayo short answer quiz, meaning to say isulti ninyo ang ang answer niya diretso. So usa lang ka mubo lang ang answer, no? Dili tag-as, no? Mga tawag na siya short answer quiz. Okay? So for example, definition of terms. Unsa na nga terms? Akong ibutang ang definition niya, then you are going to guess or you are going to answer the keywords, no? The key terms ang inyong ibutang ninyo. Nga naman yung mga short answer quiz, no? And also, we'll have computation actually, no? Okay, so we be given enough time, no? Ako man tanaw ng bananan ko ang time ninyo kung kaya ra sa inyo ang sitwasyon diha, no? Ako man gi-consider ang atong internet, then ang computation mo take man na siya og longer time sa mga katong mga basic lang o fundamental. So definitely mo na atong klase sa to ang quiz even on the finals, no? Dili ko mohatag og problem solving, pure problem solving to na sa assignment. But sa ato ang quizzes, doon na problem solving. Ang problema lang diha kay ang answer na to nakabutang siya in multiple choice. So kung mopili ka lang as ang pinaka-answer niya. Okay? So ingon na siya.
Moodle atong gamit ang platform ni quiz, sir.
Moodle.
Okay.
Okay ra sa man ng quiz sa Moodle kay dili pa kayo siya loaded na, pero sa midterm or finals usually ari ko sa MS Teams kay di gid siya madano. Magrabe gid ang Moodle kanang mag-moody gid siya, mag-moody na basta ting midterms ug finals. So ari na lang ta sa MS Teams ana, pero quizzes lang pwede ra ang Moodle. Okay? What else? Wala na ilang question?
Good afternoon, sir.
Yes.
Sir, considered as absent jud ta ako gahapon, sir.
Asa man ka ani?
Si Kanyete, sir.
Kanyete. Naka-chat
Yes,
pa ka
sir.
nako? Naka-chat ka wa?
Naka-message ko pagkagabi, sir, nga brown out sa mo.
So wala ka kasod?
Oh, sir, ako kasud gahapon.
Absent ka. Absent ka Kanyete. Kay wala man ka
Okay,
kasod.
sir.
Ang points nimo ani nga ma-plus ako at the end of after the finals na nasa 50 na lang kung I do not know how I'm going to consider that one, no? You have to find ways na lang unta to nga makakuan, no? Because sige ako na lang tanggalon, pero you are going to download the videos ato na lang katanaw sa kuan, ha? Kanyete?
Yes, sir.
Hello.
Thank you, sir.
Sige. By the way, ang late na to, if you have 3 ka lates ninyo, consider na siya nga 1 absent na basta 3 ka late. Okay? So, pag duha na ka late ninyo, ayaw dyan mo ka late na. Kay once gani malate, doon na usa ka absent. Okay? Sige. What else? Wala na? Okay, so wala na. Okay? So, God bless guys, no? You can log out now.
Thank you, sir. Thank you, sir.
Okay.
Yes, sir.